Hi, my name is Masoud, and today's presentation is Simple Baseline for Bayesian Uncertainty in Deep Learning for ECE 591. The main idea of this paper is to fit Gaussian distribution on deep networks and estimate posterior distribution. But before getting to the paper, we need to understand Bayesian networks and uncertainty. Uncertainty in statistics simply means how much confidence there is in the prediction. For instance, when models predict that a patient has cancer, what is the probability that the prediction is correct? There are variations of uncertainty. Some are intrinsic in the system, so we cannot do anything about them. Suppose you are using a stopwatch with 1-digit precision. So the stopwatch has the variance of 0.1. Also, there is extrinsic variation that caused by measurements and are out of system, like measuring the time using a stopwatch when a task is completed. Uncertainty is important because the events and the data have uncertainty. It might also be because of the lack of irrelevant variables in the model. Anyway, uncertainty is a natural quality, so the machine learning data and models have uncertainty as well. One obvious example is the randomness in the training methods. Another one can be the human biases. So it is tied to the predictions as well. And sometimes being overconfident about prediction can be harmful. A standard neural network is trained to maximize the likelihood of prediction, and overconfidently, it has one particular prediction for each input. They are powerful function approximators and have extreme flexibility due to many model parameters, the weights and the biases. The parameters can be learned from data, but what's wrong with the neural networks? Because of huge number of parameters and the flexibility, neural networks suffer from overfitting. Overfitting happens when the learning algorithm tunes the model parameters for performance on the training set by optimizing the objective function. So what is the Bayesian neural network? Bayesian neural networks combine neural network with Bayesian inference. In Bayesian inference, instead of learning the parameter values, we seek to compute the conditional distribution of the weights given the training data. In other words, we want to maximize the posterior by marginal distributions that best fit the data. Bayesian neural networks usually train a robust model and they give the whole picture of prediction, although they need longer training epochs. This figure shows the output of a Bayesian neural network model that is trained on MNIST dataset and is tested on digit 3 and letter B. For digit 3, the prediction is 3 by probability of 100%. And for letter B, since there is only 10 categories in MNIST dataset, model has to pick one of them, and the prediction is 8. But the probability is 57%. Standard networks cannot predict out-of-domain detections. There are two main categories to define uncertainty in networks, Bayesian or non-Bayesian. Bayesian inference allows us to learn a probability distribution over possible neural networks. We can approximately solve inference with a simple modification to a standard neural network tools. The resulting algorithm mitigates overfitting, enable learning from small datasets, and tells us how certain our predictions are. Markov chain Monte Carlo methods comprise a class of algorithms for sampling from a probability distribution. By constructing a Markov chain that has the desired distribution as its equilibrium distribution, one can obtain a sample of the desired distribution by recording states from the chain. The more steps that are included, the more closely the distribution of the sample matches the actual desired distribution. Various algorithms exist for constructing chain, including the Metropolis Hastings algorithm. In variational inferencing, we model the posterior directly. The actual posterior distribution should be calculated using the Bayes theorem, which is complicated. Instead, we can approximate the posterior. Given the observation X, then build a probability model Q for latent variable Z, such that Q be as same as P for Z given X. Dirac variational inference use dropout at test time from a distribution of variational parameters on existing neural networks. A peripheral network can be used in Laplace approximation, and this method will find a local distribution around theta MAP. In this approximation, we need mu and sigma to define the distribution. Mu is the theta MAP, which can be found by maximizing the negative likelihood of log p of theta given theta. Theta. And the covariance is the negative Bayesian inverse of the loss. For non-Bayesian methods, we have the ensembles method that would generate a new prediction by combining the training results on different neural networks and calculating the weighted average of the predictions. In general, ensemble benefits from the strength of several networks instead of having one powerful network. Temperature scaling is a post-processing method to fix overconfident networks. This method has a learnable parameter that affects the softmax function in the last layer. Stochastic gradient descent is an iterative method for optimizing objective function and is widely used in training networks. This formula shows the update function of SGD in each step. It has two parts, loss function and regularization. Theta represent the parameters. Eta is learning rate, B is batch size, Y is label, F theta is the network, X represent the input, and N is the number of parameters. Eta can be changed over time using the schedule. This function doesn't have any uncertainty on parameters or prediction. Stochastic weight averaging is an optimization procedure that averages multiple points along the trajectory of SGD. SWA starts from a pre-trained network or trains the network for some epochs and then keeps training the network for T epochs with a relatively high learning rate and calculates the average of weights. SGD with a high learning rate explores the set of possible solutions instead of converging to a local minimal point in the weight space. SWA significantly improves performance compared to a standard training technique. Because SWA is able to find a more centered solution and lead to better generalization, This method only requires one vector with the size of parameters. SWA can be interpreted as ensembles because the weights are the average of different points in weight space. It might be even better since it uses the wider range with better generalization and it has one network, means less computation and memory is needed. SWA is implemented in PyTorch and TensorFlow. Here you can see how you can use it in TensorFlow. There is no limitation on using SGD with SWA. Any optimizer can be used. Since we can take the first moment of iterates, why not try the second moment and calculate the variance? The sigma diag use the second moment and calculate the covariance matrix with negligible additional computation. It calculates the covariance of weights independently, so we can define a distribution for each of weights separately. This distribution is defined by a Gaussian with the mean of theta SWA and the variance of sigma diag. This approximation might not be very accurate, but it is efficient, since only requires two vectors with the size of parameters. To make it efficient, it maintains a running average of the first and second uncertain moment for every weight, and then computes the mean and covariance at the end of epoch t. The square in theta SWA and theta I are applied element-wise. A better result can be achieved by using the whole covariance matrix, but it might be expensive to use all the weights over t epochs because we need to store all the parameters of each step in the memory. And also, we don't have the access to theta SWA during the training. Instead, we can approximate theta SWA with theta bar, which is the running estimate of the parameters. One more approximation is to reduce the rank of matrix from T to K. It is like reducing the parameters dimension from number of parameters to a K. We can form D hat from the last K training epochs. K is a hyperparameter of the method, and N is the number of parameters. Now we can form the distribution of weights in swag method. The distribution is a Gaussian with the mean of theta SWA and covariance of sigma diag plus sigma low rank over 2. And to find the posterior, we can take samples from the Gaussian distribution and calculate the posterior using the sampled weights and find the posterior mean and covariance. The swag approach require k plus 2 vector of size of parameters, and the calculation have the complexity of kd, which is still the size of the network. The value of hyperparameters might be different for different architectures and different size of parameters. The suggestion of the author for their experiments for k is around 20, and for number of samples, although even with 3 or 5 number of samples, might the result be good, for a stable accuracy, a higher number is required, like 30. And a learning rate of about 0.1 to 0.01 might be good. To test the quality of the swag approximation, The article calculated the loss along the eigenvalues of covariance matrix with the distance of t from theta SWA for pre-ResNet 164 on CIFAR 100 database. It shows that the iteration of SGD contains the information of posterior distribution, and the SWAG is able to capture this information. The plot shows that the loss is bowl-shaped and gets wider for larger eigenvalues. The figures on the middle and the right show the comparison of eigenvalues V1, V2, and V3, V4. The plots visualize the negative log likelihood for different methods, databases, and models. As you can see, SWAG and SWAG-diag performed very well and have the lowest loss in most plots, and SWAG performed much better for the results of SWAG and SWAG diagonal. The complete training time is chosen to 300 epochs, and T is 140. This figure shows the reliability diagram of classification on CIFAR 100, ImageNet, and transfer task using different optimization algorithms. Dash black line shows a perfectly calibrated network which has high accuracy and high confidence. Confidence is defined by the max softmax output and means how much confidence the algorithm has for a class. Under the dashed line means underconfident, and above line is overconfident. The closer to dashed line means the better prediction. For sure, there is no perfect model which lies on the dash black line. This plot is drawn by splitting the test data into 20 bins based on the confidence for each method. So x-axis shows the median of the bin and y-axis shows the mean of the confidence minus the accuracy of the bin. As you can see, SWAG has a very good reliability on CIFAR 100 and transfer learning, and it is good on ImageNet. Multi-SWAG uses multiple independent SWAG models to form a mixture of Gaussians as an approximate posterior distribution. Different basins of attraction contains highly complementary explanation of the data. Accordingly, marginalizing over these multiple basins provides a significant boost in accuracy and uncertainty representation. Multi-SWAG can be viewed as a generalization of deep ensembles, but with performance improvement. In middle plot, you can see how multi-SWAG can beat SWAG and SGD for different V's of ResNet 18. Pay attention that this plot has 20% corruption, which means there was 20% mislabeled data in dataset. Figure right shows how increasing the number of models can affect the performance of the network. This paper shows that the SGD trajectory lies on a Gaussian distribution, and by sampling the weights and fitting them on a Gaussian, we can achieve a Bayesian neural network. Authors showed this method performed very well on image classification, but it can be used on any model and deep learning problems. Here is the all the references that I used in my presentation. And thank you for listening to my presentation.